Hello, welcome to this new video series. I try to explain this course in a detailed, structured manner. There are multiple videos following this video. Make sure that you take your time to learn and practice. There are code files, materials that are provided in the description. Make sure that you download them while you are practicing these videos. If you have any questions, you can always post them in the comments window. Thank you and good luck with the course.
Let's try to understand the theory and the intuition behind the transformers. We will also do a couple of exercises. We hear a lot about large language models. Almost all the large language models right now, what we are talking about, they all are based, most of them are based out of this transformer architecture. So in ChatGPT, T stands for transformer, generative pre-trained transformer. For us to understand large language models, either we take the theory of transformers for granted, or it's better to understand what exactly are transformers. At least a basic understanding of the transformer architecture is required. Transformer was first introduced in 2017, but later on, the whole NLP, we can say it almost revolutionized this whole NLP. From there on, we have these large language models, and you can see right now the whole field, generative AI, is kind of built on top of these large language models. It was introduced in a paper called Attention is All You Need. We will try to understand what all topics were discussed in Attention is All You Need. Definitely, this paper will be slightly difficult to understand if you see it from theory point of view. I will try to bring some analogies that will make us easy to understand this whole transformer architecture. And this paper, Attention is All You Need. Transformers topic, you cannot directly understand it as it is. There are some prerequisites. You cannot directly get started with transformer. Transformer may look like a topic, independent topic, but it is not an independent topic. For you to understand transformer, you have to be good with machine learning, or at least a couple of algorithms like linear regression, logistic regression, artificial neural networks. You have to be good with deep learning. You have to understand what are recurrent neural networks, what are long short-term memory. You have to be good with NLP. Within NLP, you have to understand what is Word2Vec, word embeddings, etc. Once you have good understanding of all these, then only you can get started with transformers. If you do not have the understanding, what I suggest is you go to my YouTube channel, you go to Venkat Reddy AI classes. In that, you go to playlist. In the playlist, you must watch machine learning first step, and then you must watch the complete deep learning as a second step. And then this is optional. You can watch generative AI course as well. But remember, without understanding those three topics, there is no point in discussing about transformers, because transformers is not a parallel or independent topic out of this. So for you to understand transformers, you have to understand deep learning. For you to understand deep learning, you have to understand machine learning. So machine learning followed by deep learning, followed by generative AI is what you have to follow. This is the whole path that you have to follow if you want to really understand transformers. Otherwise, no matter how many times we see this transformers theory, no matter how many times we go through this Attention is All You Need paper, we will not be able to get a hang of it. You got to have your basics covered perfectly. If it takes time, give it some time, complete these three, and then only you get started with transformers. Transformers are mostly used for processing sequential data. You have two types of data sets, or two or three types of data sets. One type of data set is time series data or sequential data. The other one is cross-sectional data. For example, if I am talking about a data set where there are some customers who have purchased the product, some customers are buying the product, some customers are not buying the product. So based on the customer age, based on the customer income, number of loans, etc., etc., I have the customer profile details. I want to predict my target variable, whether the customer will buy the product or not buy the product, or whether the customer will be defaulter or non-defaulter. Or given the review, I want to predict whether this review is positive review or whether this review is negative review. If I want to do these type of tasks, now this is not really time series data. Even if I change the rows, even if I interchange the rows, let us suppose row number 1 is now changed as row number 10. Row number 10 is changed as row number 15. Customer 1, whether he appears here or whether the customer 1 is kept in the second row or the third row, it doesn't really matter. Even the columns, if I interchange them, let's say here the first column is age, the second column is income. Now if I take income here, age here, it doesn't really matter. This is cross-sectional data. I have taken one cross-section of time. Maybe I have taken 6 months data of the customers, around 100,000 customers I have taken. And this data, I can shuffle it. Even the columns can be shuffled, even the rows can be shuffled. So there is no difference. But if you say time series data, if I take stock price, if I take a particular stock and its price for the last 30 days, then I cannot really shuffle it. I have to give respect to this time series. I have to make sure that this series is not changed. This is sequential data. Or I have a sequence of words with me. Based on these sequence of words, I want to predict what is the next word or what are the next set of words. Now that is also sequential data. Oh, what a lovely day. I would like to, and then what is the next word if I want to predict? I would like to go out and explore. So this is known as sequential data where we have to give preference to the sequence. You cannot just shuffle it. You cannot put one word here and one word here and the meaning itself changes. So transformers are largely where in the attention is all you need paper. They have explained sequence to sequence translation. That means language translation, sequence to sequence model prediction. So you will have language one, which is sequence of words as input, and you want to predict the translated version, which is language two, sequence of words. Similar architecture can be used for chatbots. Your question from the user is the input, a sequence of words. The answer from our chatbot is the output, a sequence of words. So transformers are used for processing sequential data. What is sequential data? It is considering the sequence of words as input. So you have to give preference to the sequence. So sequence of words, you got to give respect to the sequence. This is also a sequential data, time series data, where you are taking stock price for the last 30 days, or if you are taking sales of last 12 months. Now, if I want to take these last 12 month sales as input, if I want to predict what is the next month sales, I cannot really simply shuffle this sales data. I have to give preference to that sequence. So that is known as sequential data, which is used in transformers. Transformers are basically used for processing sequential data in language translation, text generation, taking the human text as input, which is known as prompt. Based on that, you want to generate some text. That is what we do in ChatGPT. Chatbots, conversational agents, taking the human question as the input, a sequence of words, and trying to predict what is the most possible answer. Genome sequence analysis, sound wave analysis, time series data analysis. This is all. These are all the applications of transformers. This is just an extension of encoder-decoder mechanism. Actually, in the deep learning, when you are going through deep learning, at the end, there is one more architecture that is used in handling sequential data that is known as recurrent neural networks. An advanced version of that is long short-term memory. Recurrent neural networks are mostly for short-term memory. Long short-term memory takes care of long-term memory component plus short-term memory component. In fact, we can use long short-term memory plus encoder-decoder architecture to do the language translation until we come up with transformers. One of the state of the art or one of the best algorithm that is used for doing the sequence to sequence prediction or language translation was LSTM plus encoder decoder. So we will use that encoder decoder mechanism. I'm going to explain what exactly is encoder decoder mechanism once again here, but it was clearly explained in RNN and LSTM in our course. So we will use encoder decoder mechanism and then we will get rid of this LSTM. Earlier it was LSTM plus encoder decoder for sequence to sequence model building for language translation. Now we will do the language translation by using transformers plus this encoder decoder plus something else without the use of LSTM. So I'm just telling you, introducing you some words right now. I haven't really explained you what are their meanings. We're going to get clarity throughout this session. Just hold on for a bit. As of now, you can say that transformers are the most widely used models behind almost all the large language model, be it Gemini, be it ChatGPT, be it Claude. No matter what is the large language model, whichever is the company that you are looking at that has created the large language model, mostly they have used transformers. Transformers is the reason why today Gen AI as a separate field it is existing. It was not there 5, 6 years back. Generative AI was not treated as a separate field. In fact, we don't even see people using the term generative AI. It was simply used as AI. But now, because of transformers, generation of the text was almost like human like text. That is why this whole field, generative AI, has taken birth. And the reason is transformers. So let me revise some of the important concepts before we jump on to transformers. One of the concepts that we need to revise is word embedding. So what are word embeddings? We want to convert the words into numbers, specifically numerical vectors. That is known as word embedding. None of the machine learning, deep learning models can directly work with the text data. If I'm saying that I like this, now I is a non-numerical word, non-numerical value, like is a non-numerical value, this is a non-numerical value. None of the machine learning algorithms, none of the deep learning algorithms can directly handle these type of non-numerical values. We have to convert them into numbers. Now, one way of converting them into numbers is one-hot encoding, converting each of these words into some kind of very sparse vectors. But that has a problem. One-hot encoding works when you have limited number of non-numerical values. If you have the value called region, region takes values east, west, north, south. Now, directly east, west, north, south, these non-numerical values you cannot use in analysis. If there is very high sales in south, we cannot really capture that because south is a non-numerical value. If there is very low sales in east, we cannot capture that pattern and send it to a model because this is a non-numerical value. So what we tend to do is we create something called one-hot encoded values. So we create region 1, region 2, region 3, region 4. Four distinct values are there. Four columns we will create. Each of these columns take values 0 and 1 only, either 0 or 1. So this will be filled as 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So if there is very high sales in south, this variable will capture that information. This variable will be sending that information to the model. If there is very less sales in east, then this variable will take care of it. That is how you handle non-numerical values. This is known as one-hot encoding. One-hot encoding or dummy variable creation. These are all dummy variables. However, this one-hot encoding is not meaningful if you have too many distinct words. Here there are only 4 words, so creating 4 new columns makes sense. But if there are too many values, and general English will have too many values, natural language processing will have too many words. So one-hot encoding is not the right approach if you want to really keep all the meaningful relations intact. And without losing any information, you want to convert this whole data into numerical values. So the idea is to convert our text data into numerical data with very less loss of information without introducing any additional error. For that, we have something called Word2Vec, converting words into vectors. So how Word2Vec works? Word2Vec has 2 major steps. First, we create training samples and we use these samples to train the neural network model. So the major point in Word2Vec is if king is one of the word, then it is in the context of strong and man. So when I'm converting king into a number, I have to make sure that I'm tying up that I'm somehow taking care of strong and man. I'm bringing these 2 values into picture. The words in its context must be considered when you are converting one word into a vector. Earlier, without considering these two independently, we were doing one-hot encoding because when I say king, we are talking about a particular king who is a strong man. When we are talking about queen, we are talking about a queen who is a wise woman. We are not really talking about a queen in chess game. We are not talking about a queen in playing cards or something. We are talking about a queen who is a wise woman. So what we do first is in step 1, we take word as input. King is in the context of strong and man. Input is king, output is, so input is word, output is word in the context. Input is word, word in the context is man. If you take this word strong, I'm not talking about a very strong tree. No, that is not the context. I'm not talking about a very strong coffee. No, that is not the context. I'm talking about a strong king. So strong is in the context of king. Strong is in the context of man. Similarly, when I'm talking about a man, I'm not talking about Batman or a Superman or a He-Man. I'm talking about that man who is strong. I'm talking about that man who is a king. So man is in the context of king and strong. So if you see the surrounding words, automatically you will get the context. So queen, when I talk about queen, I'm not talking about queen in the chess game. When I'm talking about queen, I'm not talking about queen in the playing cards. I'm talking about a queen who's wise. I'm talking about a queen who's a woman. Similarly, when I say wise in the context of queen and woman. When I say woman, I'm talking about a queen who is wise. So this is step 1. You create the data where the word is input and the word in the context is the output. Then you try to build a shallow neural network model. Once you build this model, in the process of building this model, you have observed that king is not connected to every word here. King is connected to strong and man. When king is input, strong and man were the output. When strong is input, king and man were the output. Similarly, when queen is input, wise and woman were the output. Strong and man were not the output. So once you build this model, once all these weights are calculated, then you supply the value of strong, whatever are the hidden layer output values, these 3 values together, they will be called as vectors. I'm just giving you a brief of Word2Vec. those, if you are already aware of Word2Vec, you can skip this and you can go further. Simply what I'm trying to say is every word will be converted into a vector and there will be meaning to this vector. In the sense, this vector of king and man will be somewhat similar. If you find cosine similarity, that will be very high here. And this word king and queen or king and woman will have very less similarity. Maybe just by observing these values, you may not get that idea. But if you try to find the cosine similarity, there will be higher similarity between king and man. There will be lower similarity between king and woman. So the words that are similar, they will fall nearby. Their vector representation will be similar. King, man, prince, strong, they will be near to each other. Queen, wise, this will be kind of near to each other. Similarly, if you see this example, I have intentionally given two different contexts. Trees are tall, trees are green, trees are majestic, trees are essential, trees are diverse, trees are oxygen giving. Computers are fast, computers are smart, computers are useful. Now, when you do a Word2Vec, it will turn out to be like this. Computers are fast, powerful, charging, trees are diverse, like useful, oxygen giving, trees, etc., etc. And the whole words. Like since this is very small data, you will see this as output. If you have a very large data, what you'll observe is the words are converted to vectors and those vectors have some meaning to them. There will be similarity. The words that are related to computers, they will have higher similarity, the vectors, and the vectors that are related to trees, they will have higher intersimilarity. So intra, it will be very high. Inter, if you try to compare the word which is related to trees, if you try to compare its similarity with the word that is related to computers, you will see a very high dissimilarity. So that is called Word2Vec. And once again, I would like you to go through Word2Vec in detail, do an exercise, then only you proceed further. Now, let us get into the point, which is transformers. The Word2Vec has some limitation. Now, from here on, important aspect is starting. So try to focus a lot. So what is the limitation of Word2Vec? Let us get an idea. Now you have a set of birds, grasshoppers, dragonfly, locust, moth, and then beetle. These are some kind of insects here. They have similar vector representation. And you have batting, bowling, scoring, fielding. This is cricket, which is a sport. Now, if I have a new word, which is cricket, now where exactly it should fall? When I say crickets chip continuously during night, it means that I'm talking about an insect. But if I say cricket is played with ball and bat, then I'm talking about cricket as a game. Now that is a problem with Word2Vec. Cricket itself, even though this is a single word itself can be seen in two contexts. There are two different contexts for the same word. Now in Word2Vec, you will not have two different vectors for the same word. So cricket will have universally single vector representation only. In Word2Vec, you will not have one word with two, three different vector representations. You will have single representation only. Now, it may be possible that a single word can be seen in multiple contexts. Sometimes, if you are building very sophisticated advanced chatbots or advanced generation or advanced search engines, you have to make sure that these different contexts should also be taken care of. But Word2Vec will give you the similar representation, not similar, exactly same. Wherever you see cricket, whether it is an insect, whether it is sport, you will have the same Word2Vec, same vector value, which seems to be counterintuitive. That should not be the case when you want to really focus on a particular context or the subcontext. Another example that I have seen is in Google, I tried searching for the code for the language translation. So what I wanted was English to French translation model GitHub code. I wanted the Python code for English to French translation. So I want the Python code where the model will take English language as input and it will convert it into French language. So I have a data set English to French, then I'll build a model and then that model will finally do the prediction. And I'm searching for the GitHub code for that. That is my intention. But what Google has understood is it has done the literal, it just looked at the translation. It found that English to French translation model GitHub code. So what Google has thought is maybe I want to do the translation from English to French for this particular phrase model GitHub code. So it has taken model GitHub code as input and it has predicted a French phrase or whatever is the translation of this. Now, this is what I want to say, that translation doesn't necessarily mean it is just the one sentence to another sentence translation. Here we want to give more emphasis, more weightage onto model GitHub code rather than simply translation. So let us see once again the Word2Vec problem. If you see the first sentence, I can bear the pain. I'm used to playing all day. That cricket bat is very light. So this is a conversation that is happening on a cricket field. Sport, cricket is a sport, and somebody is talking like this. I can bear the pain. Probably he got hurt on the cricket field. I'm used to playing all day, so that cricket bat is very light. I opened batting for my team, so he used to bat first. Always, he was an opener. So that was sentence one, totally different context, a conversation that was happening on a cricket field. Now, if I come here, it was very dark, there was no light. She opened the can, she found a bat and a cricket. Suddenly, a bear appeared behind her. This looks like a fiction novel or something, some kind of uh, scary novel. So here, if you see in this novel, this is I know this is just an extract of 4 or 5 lines or 2 lines. So here, if you see this, I can bear the pain. Here, bear means endurance. Whereas a bear appeared behind her. Here, a bear is actually a bear animal. Now, that cricket bat is very light. That means its weight is very light. It was very dark. There was no light. Here, it is, we are talking about light being dark versus light. I opened the batting for my team. Here, opening means playing first. She opened a can. So open, open, almost same. But here, I can bear the pain. Now here, this can is different. She found a bat. Here, a bat is an insect, or it's actually uh, a living being that we are talking about. But here it is an object, cricket bat. And cricket here is an insect, whereas cricket here is a sport. So what I'm trying to say here is Word2Vec. If you use this data and if you have these two different contexts, Word2Vec will give the same vector representation for this can and this can. It will give the same vector representation for this bear and this bear. It will give the same vector representation for this light and this light. That is the problem. So I can bear the pain. I can bear the pain. It will be this vector and these vectors are static. But what you will observe is the word can over here. I can bear the pain. And she opened the can. Do they have the same meaning? Not at all. Similarly, the word light here, the bat is very light versus there was no light. When we use word to vector algorithm, are we going to get the same vector or two different vectors? The answer is we will get two different vectors. We are not going to get the same vector. Now that is the problem with word to vec. What is the problem with Word2Vec? Same word can, but the context is I can to be able to a can container or the tin. Same word light, lightweight versus light in terms of vision. A bear is like endurance. I can bear the pain versus bear the animal. Word2Vec is good, but it is not perfect. Yes, Word2Vec helps us in multiple places. Somehow, even with this limitation, you can solve a lot of problems. You can get very good accuracy. Maybe without Word2Vec, if you use another technique, maybe you will get 70% accuracy. From 70% using Word2Vec, you can push it to 90%. Now we have reached a phase we want 99% accuracy or 98% accuracy. If that is the case, then Word2Vec is going to fail, especially very, very highly contextual, subcontextual nuances. Everything you want to predict with highest accuracy, almost as humans, if you want to beat humans, your model has to be very, very accurate. In those cases, Word2Vec may fail. As humans, we understand the contextual relevance and the difference between those words. When I say, I can bear the pain, I have opened a can, there's a difference we can distinguish. But the word-to-vec theory doesn't have the mechanism to differentiate these words based on their context. Both the words will have the same vector representation, and it is not going to work when you are building very large systems. We need some more contextual relevance to the existing Word2Vec. Word2Vec is good, no doubt about it. Word2Vec really works, no doubt about it. A lot of people use Word2Vec, no doubt about it. A lot of models are still using Word2Vec. But if you want to really build intelligent models, if you want to build models that are challenging humans, if you want to build intelligent chatbots, if you want to improve the search engine, if you want to like these kind of searches, we don't want to give these type of results, isn't it? If you really want accurate search engines, if you want to do language translation in the most contextually appropriate manner, if you want to really build accurate voice assistants and email filtering, we need to preserve some more context. We need to preserve some more contextual nuances. We need to capture all those subcontexts over and above the word embeddings. So let us see an example. Let us see this example, see how we can solve this problem. Right now, you can consider this as a problem. Word2Vec gives the same vector representation for all the words, no matter all the words in the sense that for the single word, whichever context it appears, you will have the same vector representation. Let us see how to solve that problem.
Continue with the next video in the playlist. We are covering everything step by step. If you have any questions or the comments, please post them in the comments window below.